Hello students, welcome to lecture 24. By the end of this class, you will be able to explain or describe the single phase semi-converter with RL load. Okay, so I hope you are with me and you are understanding that we are discussing module 3 where we are discussing phase controlled rectifiers, right? These phase control rectifiers are simple and less expensive power semiconductor circuits where the rectification efficiency will be in general above 95%. Okay. Since these rectifiers convert AC to DC, these are also called AC to DC converters. Okay, just for your information, and you should know all these terminologies because in external exam question paper, you might get questions based on different terminologies. So you should be familiar with these. So these AC to DC converters are extensively used in industrial applications where you have applications with variable speed drives, okay? So which can range from fractional horsepower to megawatt power levels, all right? So these phase converters can be broadly classified into two types, single phase converters and three phase converters, okay? And in each type can be subdivided as first semi converter, second full converter, and third dual converter. So if you are familiar, if you can recall, we have already discussed full converter and dual converter, where you know that a full converter is a two-quadrant converter and the polarity of its output voltage can be positive or negative. However, the output current of the full converter has only one polarity, mind it, yes? A dual converter, if you recall from our previous class, it is again a four-quadrant converter where both the output voltage and current can be either positive or negative, right? So, the semi-converter, as you can see, which is a first category, but I'm following the syllabus specified. So semi-converter is a one-quadrant converter and it has only one polarity of the output voltage or the current, all right? So this is the general block diagram what you can refer to. So as you can see, the one quadrant converter is our semi converter, wherein in this converter you can have thyristor and diode, okay, and the output will be only in first quadrant, that is the output voltage and current will have only one polarity, okay. The two quadrant converter, which is nothing but the full converter, as you can observe, the output voltage can be positive or negative. However, the current will have only one polarity, that is positive, right? And in dual converter, which is a four quadrant converter, as you can see in the figure here, the output of which can be, that is the voltage and current both can be either positive or negative based on its performance, whether it is performing or used as a rectification or inversion, right, which we have discussed in the previous class. So in this class you will be understanding the performance or working of semi-converter, all right. So going to the circuit diagram, this is the single phase semi-converter. Observe the circuit there. The circuit is shown here, which is highly inductive. So in all these discussions what we are having in this chapter, it is assumed that the load is highly inductive, okay, and the load current will be continuous and will have a negligible ripple, okay. So assuming these basic assumptions, we'll go with the understanding the working of semi-converter. So as you can see, the load is inductive. There is RL load, and it is assumed that the load current is continuous. All right. So if you observe the circuit there, you have T1 and T2. There are two thyristors, and you have D1 and D2, two diodes in the circuit. Okay. So though the circuit is of full wave, but you have two thyristors and two diodes. That's why the name semi converter. Okay. Though it is a say full wave conversion, what we are expecting, full wave rectification, all right, where we are expecting output from both the half cycles, but because there are only two thyristors, which is a output controlling devices, it is semi half converter, because you are not able to completely control the output. Okay, so there is only two power semiconductor device there and two normal diodes. All right, and as you can observe, there is one special diode which is a freewheeling diode. The significance of freewheeling diode in the circuit is that it helps in maintaining the continuity of the current, the output current. So in other words, if we have to say in a simple words, this freewheeling diode will keep the output current uniform. All right. So let's observe how it happens. Okay, working of this circuit. So observe the circuit there in the positive half cycle. If you see that first T1 will be forward biased, and again you have to remember for both of these power semiconductor device, you need the gate triggering circuit, which is not shown here, but gate triggering circuit will be there, which will control the time at which you are firing these two thyristors, T1 and T2. Okay, remember that. So whenever thyristors are used, there will be gate triggering circuit, but it is not shown here because we are concentrating on the working of the complete converter as such, which is a semi-converter here. Okay, so in the positive half cycle, when the voltage is sufficient enough to forward bias this T1, and when there is a sufficient triggering voltage given at the gate terminal, say T1 conducts, right? So when T1 is fired, the circuit completes, isn't it? The voltage what you apply here, it appears at the load. So how will be the current flow? Observe that it will be from T1 via load, right, and D2, isn't it? So this will be the path of the current, right? The circuit completes from, this is your source, T1, load, and D2. So that is how the circuit completes. Okay. So assuming that, say in the positive half cycle, thyristor T1 is forward biased. So when thyristor T1 is fired at, say, at some firing angle alpha, okay, omega t is equal to alpha. Now the load is connected to the input supply via T1 and D2, isn't it? So during, say, time period between alpha and pi, let's observe the waveforms in a shorter while now. Okay, so say between the moment the input signal becomes negative here, okay, when the input signal is negative here, what happens, that is the time when the freewheeling diode DM will be forward biased. All right, so the energy that is stored in the inductor will be bypassed or fed, or it is uh, allowed to flow through this freewheeling diode, which is now conducting. Okay, so that will cause T1 and D2 to turn off during the negative cycle. I hope you are with me. I'll repeat. In the first positive cycle, when T1 is fired, the current path will be from T1 load D2, so that will complete the circuit. Okay, the moment the voltage is just crossing below 0, so when the input signal is going negative, so that is when the freewheeling diode will be forward biased. Okay, so we know that in the negative cycle T1 will be reverse bias and it should turn off, right? So the energy that is stored in the inductor, it has to flow somewhere, right? So that is where the freewheeling diode will come into picture and it will allow the current to flow through this path. Okay, so in the negative cycle of the input, as you can see, when you give a triggering or the signal to say T2, okay, T2, the thyristor 2, so that will conduct in the next half cycle. Okay, say you have triggered T2 at pi plus alpha, all right. So from pi plus alpha, the path for the current to flow will be T2 load and D1. Okay, this will be the path. Okay, so again, when the input signal reverses, that will when the energy stored in the inductor will be passed through the freewheeling diode. So what is the role of the freewheeling diode? It maintains the continuity of the output current, all right? Because there is shifting from positive to negative, right? Polarity shift. So the T1 and D2 will be conducting for shorter period of time and T2 and D1 will be conducting. Okay, so during that break, when there is change or shifting of polarity, that is when freewheeling diode will be allowing the energy stored in the inductor to flow. Okay, so that is the significance of this freewheeling diode. So what happens? Actually, this type of converter, it has a better power factor, okay, because of this freewheeling diode, and it is mainly used in the applications where you have to have a power up to 15 kilowatts. All right. So let us discuss the waveforms there. Okay, observe the waveforms. So here is your input Vm or V is your input, which is given as Vm sin omega t. All right, and assuming that in the first half cycle from between 0 to pi, say at alpha you have triggered T1. Okay, so when T1 is triggered, the input appears at output. So this is your output V naught. All right, so output you are getting between alpha to pi, right? So you can see that this is your current due to thyristor 1. This is the current due to thyristor 1, which is shown here. All right. Then when T1 is conducting, you know that T2 will be conducting. So at the same time duration, if you observe here, ID2, it is expressed here. ID2 is shown here. Okay. Okay. Then in the negative cycle, in the negative half cycle, assuming that at pi plus alpha time, you have triggered thyristor T2. Okay. So should I take that? Let me check. I'll bring the circuit diagram here. I'll bring the circuit diagram here in the next slide. Okay, that will help you to understand the working of the circuit. Okay, yes, fine. So here, if you observe at pi plus alpha 2, this time instant, you have triggered T2. So when you have triggered T2, the load is connected to the supply. So you are getting this output. Okay, all right. So the output is shown here. And observe the current of thyristor 2. This is IT2. This is the current represented here. And when T2 is conducting, D1 diode will be completing the circuit. And the current due to diode 1 is shown here. Okay, so this is IT1, ID2, D2, and this is IT2, and this is ID1. All right. So let us observe this IA, which is nothing but our output current. Okay, so output current or the current taken from the supply. Okay, that is the current taken from the supply. Observe here in the waveform. All right, so between alpha to pi, as you can see, the current here is because of T1 and D2 conducting, isn't it? So the path of the direction of the current is, say, from the supply T1, from the load, and D2. It completes here. So the direction of the path of the current in the circuit when T1 and D2 are conducting, it is same as the reference direction of the source, right? So the output what you are getting is same, that is positive. So this is represented because of when T1 and D2 are conducting. This is the current. Okay. Now observe in the negative cycle when input is reversed. Now T2 and D1 will be conducting. Observe the direction there. T2, load, D2. Okay, and here. So the direction of the current here is now reversed to the or opposite to the reference current or reference direction of the source, isn't it? So this is the current because of T2 and D1 conducting this current. Okay, I hope you are able to follow the mouse there. Okay, yes, so this is the current, and the output current I naught, what you can see here, it is shown here as a straight line, but mind it again, in the beginning I had told that all the working, it is assumed that the current is continuous, but for your information, let me tell you, because the load is RL type, the current will not be straight line like this. So what happens whenever the semiconductor device T1 is turned on, when you are getting output, the current will gradually increase here at this point. Gradually increase, okay? And during this period, it will be slowly, gradually decreasing. Why? Because of the inductive in nature. Because the energy stored in the inductor will be now flowing in this circuit, right? So here when the thyristor is conducting, current will be gradually increasing, and in this period between say pi to pi plus alpha, it will be slowly decreasing because of the inductive load, and again from pi plus alpha when T2 is triggered, current again will gradually increase. So the energy is slowly stored up in the load, right? So the current is slowly building up. So it is like variation, increasing, decreasing, increasing, decreasing in the fashion. So assuming that that ripple is very negligible, yeah, the ripple content is very negligible. Why? Assuming that again, because the load is highly inductive. When the load is highly inductive, then the time constant RL will be high, right? So that will give a very smooth curve. So ignoring that ripple, here it is shown as a straight line. Okay, so that is about the waveforms. That's about the waveforms. And what the average output voltage, as you can see here, it can be expressed as VDC. Okay, taking for the first half cycle, so taking as 2 by 2 pi. So between the limits alpha to pi, your input signal is Vm sin omega t. Okay, integrating between the limits alpha and pi. All right. So substituting or applying the limits, you will get Vm by pi 1 plus cos alpha, which is your average output voltage. So the RMS output voltage, again, if you substitute Vm square sine square omega t under square root, so Vm square sine square omega t can be written as 1 minus cos 2 omega t by 2, right? So taking it outside here and applying limits, so Vrms it is given by Vm by root 2, 1 by pi, within brackets pi minus alpha plus sine 2 alpha by 2, that is again under the square root sign. Alright, so that is about the semiconductor wherein semi-converter wherein the operation of this type of converter is that the output will have only one polarity. It will be positive for both output voltage and output current. Okay. Now you have a homework here. So let me go back to the waveforms. Yes. So in this waveform, the homework for you is I want you to draw the voltage across T1 and T2. Okay. So in this waveforms, what you have here, it is represented. You have this input, you have the output voltage, and different currents of different devices. That is thyristor 1, thyristor 2, diode 1, diode 2 is shown. The current taken from the supply and the output current is shown here, and as well the freewheeling diode is also indicated. Now your homework is you will draw the voltage across thyristor 1 and thyristor 2 with respect to the input shown here. Okay, and you will submit it by say Monday, that is 16th, right? So your assignments, that is your assignment, that is waveform representing showing the voltage across T1 and T2, it will reach me by Monday. Okay. I will share you, in the canvas it will be indicated. You will upload your say your A4 sheet, the scanned A4 sheet with the waveforms drawn. All right. So you'll upload that. So go through the circuit here, the converter circuit. If you have any query, you can get back to me. And again, I repeat, please go through the e-textbook work which I had shared earlier in Canvas. It is available there, the Rashid textbook, where you can go through some of the example problems there, solved example problems, which will help you to understand the working of these circuits with the derivations, expression, etc. Okay. All right. See you in the next session.